Hi, my name is David. In this video, we are going to look at another example to get some intuitive understanding of what a p-value is. In this case, when the outcome, the metric that we look at is continuous. So again, this is another example from Peter Dalgaard's book. They're called Introductory Statistics with R. And there's this example where you look at the daily intake of something, and these are the values that are given in the book. There are 11 of them. And the question that you are interested in is whether this is consistent with the hypothetical mean being equal to, I think it's 7725 or something like that. I suppose you could plot the histogram of these. It doesn't tell you much, to be honest, because there are so few values. This could be drawn from a normal distribution, or maybe not. You don't really know, and you certainly cannot say anything about the mean. We're going to need a few things here, so we're going to definitely need to know the mean of the sample. It's 6753. We are also going to need to know the empirical standard deviation, which is a little bit over 1000. So the traditional way, of course, you can apply a t-test to this, and I'm going to show you how to do this. T-test of intake, and you're testing against the, it's mu equals h mean, and we are going to restrict our attention to when the alternative is less than the mean. So in this case, we get a p-value of 0.009. So it is significant. But the question is really, what does this really mean? And this is what we're going to explore in this video. So what the t-test is doing behind your back is it's computing some statistic from the data. And in this case, the t-statistic, it's simply taking the mean of your intake. Actually, we already have it. So m minus the hypothetical mean, and this gets divided by the empirical standard deviation times the square root of the number of elements. I think we can capture this here because we're going to use it quite often, and n should be 11, right? So square root of n. So this is the t-statistic of the sample, minus 0.25. So the question is, the real question is if this is statistically significantly less than 0. Okay, so of course you can look this up from this table of t-test values, but here we're going to show you how to get this empirically. So the p-value says that under the null hypothesis, so assuming that the data really comes from a population whose mean is 7725, then the p-value is really the probability that you would get t statistic as small as extreme or more extreme than this value here. So there's an easy way to get an approximation of this value, which is just to simulate the null hypothesis over and over again. So if we generate a large number of samples from the null hypothesis, then you can essentially look at how many of them have t statistics as extreme as this, and the proportion of those that do are a very good approximation of the p-value. So we're going to do that. So the way that many people do this is you will often see people use the matrix function for those kinds of things. So the idea is to generate a rectangular matrix with as many columns as the units in the original data and as many rows as you want. So this would typically look like our norm, and would be, well, you need to know, okay, let's say you want to generate 10,000 samples. So there will be 10,000 rows times the number of columns, so n. So you need 10,000 times n values drawn from the normal distribution. What's the other one? Mean would be the hypothetical mean. And you also need to specify the standard deviation of the normal distribution. In this case, this would be S. And then you need to tell R that this should be rearranged in such a way that there will be n columns. There you go. And as you can see, okay, it doesn't quite fit the screen here, but it has generated a matrix with, well, 5 plus 1 column, so 11 columns in total. And then what people typically do, you know, they use some combination of apply or I think the other one is sweep or functions like this that don't really tell you exactly what's going on under the hood here. But I think it's better to do it a slightly different way, and I'm going to show you how. So let's first think a little bit. What do we want to do for each row, really? Well, each row is given by just generating n values, still with the mean of h mean, the standard deviation of S. So when I do this, this generates one simulation from this hypothetical, from this distribution, assuming that the null hypothesis is correct. Okay. Now, what you wanna do, you wanna compute the t statistic of this particular row here. So the way that you do this is, let me see now. I'm gonna enclose this in curly braces. I'm gonna call this sim, and then the t statistic is simply mean of sim minus h mean divided by the standard deviation of the simulated values times square root of n, close the curly brace. So this is an R expression, and if I run this over and over again, it will generate different values. So these are values of the t statistic that are drawn from the distribution, assuming that the null hypothesis is the true one. So I want to do this many times, like 10,000 times, right? And in R, there's an amazing function that lets you do this. I'm gonna just assign the results to sim team test. It's called replicate. So replicate takes an argument and the number of times you want to do this. And the second argument is an R expression. Well, we already have the expression. Let me see if I can reformat this a little bit. No, it doesn't want to. Okay, fine. So what this is doing is that it will take this expression here and it will re-evaluate it 10,000 times. And this is really only possible because of R's non-standard evaluation feature. So if you do this, it finishes almost instantaneously. You can see the value here. This is a vector of 10,000 values. If you were to plot it, what do we see here? Oh, there you go. So you see this distribution here, and this is not a normal distribution. This is a t distribution. So these are the values that are drawn from this distribution, assuming that the null hypothesis is correct. And we remember that we had thought we had it somewhere. No, maybe we don't. Oh yeah, let's assign our t statistic to t. So t is minus 0.25. So let's let's add a line here. I think we need to do, it's a vertical line at t. Gonna color it in red. Oh, col. Yes. Okay, so you see here, this is the value that we get from the original sample. And as you can see, it's very low compared to the rest of the distribution. So there's visually there's some evidence that that the true mean is not the one specified by the null distribution, by the null hypothesis. And the way to test this formally is simply let's count how many of those 10,000 samples are actually as extreme as this one that we have here. And this is super easy to do in R, because if you type sim t-test less or equal to t, this is going to give you a Boolean vector with a true value for each item that's less than t. And as you will probably know, if you take the mean of a Boolean vector in R, it will actually give you the proportion of values that are true, because it will implicitly convert everything to ones and zeros. So if you do the mean here, it gives you 0.009. So this is the proportion of samples generated under the null hypothesis that are as extreme as the values we saw in our data. And this is the p-value. And let's just look at this guy again. You see, we computed the 0.0094. The quote-unquote true p-value is 0.009. There's some difference because, yeah, obviously because we are simulating things, but as you can see, the difference is negligible. And this is how you get a p-value for the t-test manually. And the cool thing about this is that you really understand what's going on here. Because I had to type R norm, I understand that this p-value is only valid if the null hypothesis is correct. And what does that mean? That means not only that the mean is this hypothetical mean that I specified it, that's only part of the story. The other part of the null hypothesis is that the data comes from a normal distribution where every unit is independently and identically distributed. So I hope you found this useful, and I'll see you again next time.